In this section, we'll be going over lesson 3.2, linear functions. Now, these are the objectives. Pause and take a look at them. And again, linear functions by definition would be a straight line. And as we look at some of the material we've had before, there in function form is the slope-intercept, and linear would be equations that are to the first degree. Now, generally speaking, when we think of slope, let's do a quick review. Here we see this first graph, the black line, indicates positive slope. It's starting low, and as it moves to the right, it goes up. This one starts high, and as it goes to the right, moves down. This would be negative slope. And the equation for these would be basically this. Y equals the slope times x plus a y-intercept, which would be right there. Now, these two are special forms where you may recall a horizontal line has the equation y equals b, which is that same b, that y-intercept, while this one doesn't have a y-intercept and is x equals a. And this is not a function because it does not pass the vertical line test. So reviewing slope of what we're going to be doing. Now we're asked to consider this function if we were to make a t-chart, would look like so, but using some of our other techniques in plotting this graph, our y-intercept is a positive 5, which is right there. Our slope is a negative 3 over 1. So we would go to the left 1, that would be our run, and then our rise 3 would give us this second point. And these are illustrated in the t-chart. This is something we've covered before. We're also keeping in mind that there's an infinite number of points along this line. We're just highlighting some of them. So in now example 1, we are featuring these two examples. Here this is in slope-intercept form, and you may recall this one is that special y equals b, which would be a horizontal line. So let's take a moment to plot these. In the first case, our y-intercept is a positive 2 that we see here. Our slope is a 3 over 1, so over 1 for the run, up 3 for the rise, and there's our second point. So pretty much straightforward. In part B, again, a horizontal line, y equals b. Our b value is 3, our y-intercept, so right there would be a horizontal line going through this. Now, we might do a little review here. What is the domain of this function? Well, it would be all real numbers from negative infinity to positive infinity. But what is the range now? The range is just going to be 3. A little review. Now, in example 2, we're asked to find the linear function of this particular graph. So again, we're using basically slope-intercept here, that in its function form is f of x equals. So looking at the graph, what will be our b value here? It's a positive 4. We have to put the x in there. And what we have to determine now is what is the slope. Well, here's a point right there. It's going over 2 and up this much. Or we can go over 1 and up here. So our denominator is going to be a 1, but since it's going to the left, it'll be a negative something, and our y value is up 2. So we don't write the 1. Our function form then of this would be a negative 2x plus 4. And if we went this way, over 2, up 4, that would still reduce to a negative 2. And we see it there. Another important part of analyzing linear growth is linear regression. Now, what does this refer to? Well, as we look at this graph, we see a number of points, and they're not in a straight line. But if someone wanted to analyze this and get sort of a general trend of what's going on here, you might suggest this. That is, sort of eyeballing what would be a straight line that would sort of average out what these would look like. So the person doing it might think, well, that's okay, but scrolling down, we see we could plot and get the actual coordinates of all these points. Scrolling down a little more. But again, it would be somewhat imprecise eyeballing it. And again, if you had lots of data, different people might get a lot of different lines here. So mathematicians have come up with a process that's called regression analysis. So looking this over, what is regression analysis? Well, there are various methods used, but one of the most common is called the least square method. We are going to see the formula for this, the least square method, and they say its derivation is best left to a more advanced course. But basically, it's to calculate the mean, the average of your x values, the average of your y values, and they're illustrating that here. You have your data points. You're taking the sum of them, dividing by the number that you have, and then rounding it to 6 decimal places. Do that for the x, do that for the y. This gives you what is called a delta value, and this little Greek triangular symbol relates to that. What's the delta value? It's the mean, the average of your x values and the average of your y values. And then they've put it in this rather extensive table. And then you square them, find the difference, and notice it gets to be rather complex and detailed. And then you determine from this the slope. That would be y values over x values, and that gives you a slope value here, which is then used in setting up the equation and then figuring out, using some sets, what your y-intercept would have been. As you see, it's quite a complex process, and fortunately, we're able to use a calculator to figure this out, if that calculator has that particular function. Now, the proof of the pudding is to see if you can take this information and find, using linear regression, the graph of the line that best fits this data, and then later the Pearson correlation coefficient for the letter R. So as we look at this, you would need to define the coordinates of these points. And I see I left this one out. So let's put that in there now. This would be a 2 and a 4. Okay. So you will need these to move on to the next part. So you're going to take your x values and find the mean of these, which is 2 for the x, and the mean for the y is 3.6. Now you're going to set up a table in which you're going to subtract the mean of x, which is a 2, from your x values. And I'll show you that here. So there's the mean, 2, but it's minus this mean. So a minus 2 and a negative 2 is a negative 3. A 1 and a negative 2 is a negative 1, and so on. And here we're going to do the subtraction of 3.6 from each of these and get this column. Okay, again, there's a lot of tedious work going on here. Let's go down to our next column, where we now bring in this value from this chart is over here. So there's our negative 3 down here, delta of x. Our delta of y is there. And we then square the delta of x. The negative 3 becomes a 9. The 2.4 squared becomes this. And we need to multiply this times this to give us this value. And we do that now for each of these. We get our data completed. Now we add up this column and we get 20. This is delta x squared. Here is the product, negative 18, adding up this column. Adding up delta y squared gives us this. Now, what do? Let's just move this down a little bit more. We take the product of this divided by, that would be this, which gives us a negative 0.9. Now, if we use this as our slope and take one of the points, we could figure out what our y-intercept might be. And here it looks like 5.4. And a slope of a negative 0.9, which is just a little less than a negative 1. And plotting that with a 5, this is our y-intercept here, going up, we're saying is 5.4, right about there, over 0.9, or over 1, I should say, going up 0.9. Again, some of this gets to be rather tedious. And then to find the R coefficient, taking these values, the sum of the product of delta x and delta y divided by this gives you another value close to a 0.9, but this is closer to a 0.1. The fact that R is negative reflects the fact that the slope of the best fitting line is negative. And the fact that R is relatively close to 1 in magnitude means that this line of best fit is a reasonably good model of the behavior of the points. And you could have almost eyeballed this, but this would be the way to do it mathematically. Again, quite tedious. Example 4 is done in a similar way. And until you get your hands on to try it, and again, look at these notes carefully. And of course, you can use the learn that's in your lesson to follow that. We'll just briefly show it here. Again, what type of slope does this look like? Is this going to be a positive line or a negative line? Again, this one would be hard, but you get your ordered pairs, you find the mean, you set up your tables, put it into the formula, and they're saying that it's a actually slight positive slope that is like 6/100ths or 68 thousandths of a positive slope. And here we see the function in slope-intercept form. Again, until you try it and look specifically at an example that you're going to do. Now, an interesting thing in all of this is that if your calculator supports finding regression function, then this is going to be the ideal way to do it, because by just plugging in your ordered pairs, all of this is developed. Now, I'm not going to go over this, but it is in your Learn, and we see it here. All right, let's wrap this up. Hopefully helpful.